Hey, and welcome to my first video on discrete calculus, where we will explore the beginnings of a calculus you may not have seen before. Before we begin, I'll give just a quick disclaimer about the prereqs. I try to make my videos as accessible as possible, but sometimes some prior knowledge is important to understand the concepts we talk about. While all of the math in this video is doable with high school algebra, an understanding of some basic calculus is pretty important to understand why this video is cool. As such, I recommend knowing the basics of sequences and series, the definitions of derivatives and integrals, and basic differentiation and integration formulas. That's it. Let's get to it. So let's say we have some function defined like this. F of x is equal to 2 times f of x minus 1 for x is not equal to 0, or 1 for x is equal to 0. And for some reason we want to get some idea of a rate of change. Maybe this function represents a population size on a given day, and you want to get an idea of how fast the population is growing. Well, when you want the rate of change of a function, you take the derivative. So no problem, we'll plug our function into the definition of a derivative, which we know to be this. It isn't immediately obvious how to apply this definition since we don't have a simple expression that we can use to generate specific values of the function. Specifically, we have a recursively defined function, which means that in order to evaluate the function, we need to know other evaluations of the function. If we are stubborn, however, we might decide to start with some approximations of the derivative at x equals 1. Instead of a limit, let's approximate with h equals 1. So here are our x's and here are our h's. So first, f of 1 plus 1 is obviously f of 2. And now our 1 in the denominator doesn't really matter. So f of 2 from the definition is 2 times f of 1. So now this becomes f of 1. And then f of 1 is 2 times f of 0. And f of 0 is 1. So our derivative approximation at x equals 1 is 2. We could also try a better approximation with h equals a half. As you might be able to tell, attempting to evaluate this will be a problem. If we isolate f of 1 plus a half, we get stuck in a loop trying to subtract 1 from a non-integer until it becomes a natural number. So f of 1 plus a half is equal to 2 times f of a half is equal to 4 times f of minus a half is equal to 8 times f of minus 3 halves is equal to 16 times f of minus 5 halves, and so on. We can never find a value for f of 1 plus a half, or really f of x for any x that isn't an integer, and it's even somewhat fishy to define f of x for negative integers. This means our function is inherently discrete, which does not mesh nicely with our normal calculus. The formal definition of a derivative is built for continuous functions, and it only works when f of x is defined in some neighborhood around values of x. We don't need to give up though. We had an approximation of the derivative by setting h equal to a constant, so perhaps we can use that to come up with a new and discrete derivative that works for sequences. Ultimately, we will discover that along with such a derivative, we can create a whole new calculus to go along with it, with ideas analogous to many of the concepts in continuous calculus. With that in mind, let's create a new operator that mirrors the continuous derivative but works with sequences. First, let's replace our calculus notation with a new symbol. Let's use a capital delta, since the derivative represents change in a function and delta is normally used to represent change. Then, let's get rid of this limit and assign h to a constant subscript of our operator. Then, since we're really working with sequences instead of functions, let's replace the function notation with sequence notation and replace the x's with n's and the f's with a's. Now we have an operator which we will call the forward difference operator. For convenience, we'll let the subscript default to 1, since for now we're going to focus on integer sequences like the one at the beginning of the video. So from now on, delta of a of n is equal to a of n plus 1 minus a of n. As a side note, there are other ways we could have defined the derivative analog in discrete calculus, including the backwards difference operator or the central difference operator. And further, some authors choose to drop the h in the denominator of their definitions, so pay attention to the conventions used in any particular scenario. Generally, when the forward difference operator is used to approximate derivatives, the denominator is kept, but in physical applications where the constant is equivalent to a change in units, the subscript is often dropped. So now that we have a candidate for the discrete analog of the derivative, a next logical step would be to find the discrete analog of an integral. Since our discrete derivative originated from approximations of the continuous derivative, we might look towards approximations of the continuous integral to get inspiration for our discrete integral. One such approximation is a Riemann sum. This is a left Riemann sum within subdivisions symbolically. This corresponds to dividing the interval a to b into n intervals of length b minus a over n, and using the leftmost value as an approximation for the value of the function across the entire interval. As we use larger and larger values of n, the Riemann sum converges to the actual integral. When adapting the Riemann sum for use with integer sequences, we need the length of our subintervals to be exactly 1, since we can only evaluate our function at integer values. For the same reason, we need to restrict the values of a and b to be integers as well. This means we can find an exact value of n for any given a and b. Because the length of our intervals is b minus a over n, we set b minus a over n equal to 1. Then we multiply both sides by n, and we get the expression that we were looking for. Now let's use this as our value of n in the left Riemann sum. After we cancel out some terms, this immediately looks much nicer. But we can make it even better. We can add a to the top and bottom indices of the sum, and then subtract a from all the uses of the indices inside the sum without changing its value. After some more cancellation, this becomes even nicer. Finally, we can replace the function notation with sequence notation, and we're done. Except we probably shouldn't keep using a of n for our sequence, since the constant a is the lower bound of the sum. Let's replace our sequence a with sequence y, because why not y? Okay, sorry. So we get the sum from k equals a to b minus 1 of y of k. Amazingly, this is just a plain old sum. As such, we aren't going to create a new notation for our discrete integral, as there are already way too many different notations for identical concepts in mathematics. Now, before we get all excited, we should confirm that our discrete integral actually makes sense. We know by the fundamental theorem of integral calculus that the integral is the inverse of the derivative, and ideally we want a similar property for our discrete integral. In symbols, this is the property we're searching for an analog to. We can rewrite this property into the notation of our new calculus. Let's confirm this property by expanding out the definition of our forward difference operator. So first we'll break apart the sum, then we'll shift the indices of the first sum, then do some cancellation, and then finally, every term except the top term of the first sum and the bottom term of the second sum cancel out, so we end up with this. The sum from k equals a to b minus 1 of delta y of k is equal to y of b minus y of a. Awesome, that's exactly what we were hoping for. Note that we could have chosen a different length to use for the subintervals of our integral, which would result in a different value for n and a different and slightly less pretty definition of the integral. In order for the resulting integral to be the correct inverse of the forward difference operator, the length of the interval should correspond to the value of h chosen in the definition of the forward difference operator. At this point, it might be reasonable to ask why we're doing any of this. My preferred answer is that it's hella cool, which is why I plan on making many different videos about this topic. Some truly incredible properties appear out of discrete calculus, and the wonderful thing is, integer sequences are often a lot easier to wrap our heads around than continuous functions with an uncountable amount of values. Since the structure of our discrete calculus ends up being the same as the structure for integral calculus, I often find myself starting with the discrete analog of a challenging problem in analysis in order to solve it. You'll see more about that later, but for now I'm going to give you just a taste of one of the most useful properties of discrete calculus, solving for explicit terms of recurrence relations, just like the one we talked about at the beginning of the video. Recurrence relations heavily mirror differential equations from continuous calculus, so we apply similar strategies to both. As an example of a simple recurrence relation, you are likely told in one of your algebra classes that the recurrence relation a of n plus 1 is equal to a of n plus c for some constant c, also known as an arithmetic sequence, means that a of n is equal to n times c plus a of 0. We can prove this with our discrete calculus. Let's take a look. First, we subtract a of n from both sides. Then we recall that the left-hand side is our definition of the forward difference operator. We can now solve this easily because we know the inverse of the forward difference operator is a sum. So we sum both sides from k equals 0 to n minus 1, and then we apply the fundamental theorem of discrete calculus. We're almost there. Since there are n integers between 0 and n minus 1, the right-hand side of our equation represents adding c to itself n times, which is the exact same thing as multiplying n times c. Finally, we can add a of 0 to both sides to get the expression we were looking for. A of n is equal to n times c plus a of 0. While we're at it, let's try another one. How about this one? A of n plus 1 is equal to a of n plus r to the n for some r greater than 1. We'll do more or less the same process. So first subtract a of n from both sides, and then apply the definition of the forward difference operator, and then sum both sides from k equals 0 to n minus 1, and then apply the fundamental theorem of discrete calculus, and then hopefully we should recognize the right-hand side as the partial sum for a geometric series, which we know is r to the n minus 1 over r minus 1. If you don't recognize that formula from an algebra class, don't worry. It's fairly easy to come up with. Basically, set the sum equal to some variable s, multiply it by r, and then subtract the original sum s from it. Try it out if you need to. I've linked a video about it in the description, but let me know in the comments if you need any help. So let's apply the formula. And then we'll add a of 0 to both sides. So a of n is equal to r to the n minus 1 over r minus 1 plus a of 0. Although that was still fairly neat, it wasn't that much cooler than the first example. Unfortunately, this is about as interesting of a recurrence relation as we can solve with our current tools. But don't fret, so far we only have the basic derivative and integral, and that's it. There are plenty more tools to discover and plenty more videos coming. I don't feel like stopping now though, so let's try to find a few more tools. Let's try taking the forward difference of a sequence multiplied by a constant. We'd expect something like this from continuous calculus. We can evaluate this by expanding the definition of the forward difference operator. Then we can factor out the c, and then apply the definition of the forward difference operator in the other direction. So delta of c times a of n is equal to c times delta a of n. Awesome, that's exactly what we'd expect. You can move constants in and out of a forward difference. Let's try the forward difference of a sum of two sequences. And again, we'd expect something like this from continuous calculus. Just like last time, we first expand the definition of the forward difference operator, and then we'll distribute this negative. Then we'll regroup some terms, and then we'll apply the definition of the forward difference operator, this time twice. So delta of a of n plus b of n is equal to delta of a of n plus delta of b of n. Again, awesome. That's exactly what we'd expect as well. As a side note, this means that the forward difference operator is a linear operator, just like the normal derivative. We know that the discrete integral is linear as well, because that's just a plain old sum. Let's try something more complicated, like the product rule. First, we'll look at the product rule from continuous calculus, and then we'll go ahead and start solving. Again, we'll just apply the definition of the forward difference operator. And now this time we're going to add some funky version of 0. And then we're going to reorder some terms. And then we'll factor out the b of n and the a of n plus 1. And then we'll apply the definition of the forward difference operator 2 times again. So delta a of n times b of n is equal to b of n times delta a of n plus a of n plus 1 times delta b of n. Now that looks a good bit like the product rule from continuous calculus. In fact, that 1 corresponds to the value of h we chose. So the smaller and smaller values of h we use, the closer the discrete product rule is to the continuous product rule. One slightly annoying thing about this product rule is that it isn't symmetric. We can fix that though. It just doesn't look as much like the normal product rule. So again, we'll add some funky version of 0, then reorder some terms. Then we'll factor out this delta b, and then we can apply the definition of the forward difference operator. We get that delta a of n times b of n is also equal to b of n times delta a of n plus a of n times delta b of n plus delta a of n times delta b of n. Because this is the same as our other product rule, this converges to the continuous product rule as h becomes smaller and smaller, although it isn't as obvious to see why in this form. When you work out the derivation without any specific h, there ends up being an extra h multiplied by the final term. This is analogous to writing the continuous product rule like this. If the differential operator is thought of as the tiny change in operator, the two tiny changes multiplied by each other converge to 0 faster than the tiny change in the denominator. So the last term converges to 0. This is the same way 3 Blue 1 Brown describes deriving the product rule for continuous functions, so I will link his video on the product rule in the description. Okay, just because we can, let's do the most obnoxious one, the analog of integration by parts, summation by parts. I know, it's scary, but it's also annoyingly useful. So we want a decent-ish expression for the following sum. And for reference, I'll throw up the integration by parts formula as well. Let's expand the definition of the forward difference operator and see what we can do. So first we'll split apart these sums. And then again, we're going to add some funky version of 0. Then we'll reorder some terms. Then we're going to combine each of the sums on the top and bottom line. In the case of the bottom line, we're going to factor out this x of n plus 1 as well. Then we'll factor out a negative. So now we can apply the definition of the forward difference operator 2 different times. And then we'll go ahead and apply the fundamental theorem of discrete calculus. And we're done. The sum from n equals a to v minus 1 of y of n times delta x of n is equal to y of n times x of n evaluated from n equals a to b minus the sum from n equals a to b minus 1 of x of n plus 1 times delta y of n. So that's basically the same thing as integration by parts. The shift in x corresponds to the value chosen for h, so this converges to the integration by parts formula for smaller and smaller values of h. Well, alright, I think that's enough for this video, but there are plenty of other awesome properties of this new discrete calculus, so I'll have more videos coming, including one where we solve the recurrence relation I presented at the start of the video. I should note that discrete calculus is also called the calculus of finite differences, since we're taking the difference of terms at a finite offset. In fact, the calculus of finite differences is probably a more common term. I'm just not a fan of it because it doesn't sound as cool. Well, anyway, thanks for watching. I'll catch you in the next one.